Okay. Yep. Thanks everyone for joining. We're going to hear from Professor Mike Behrenfeld from the Oregon State University. Mike is a professor in the Department of Botany and Plant Pathology. Mike's research interests, as very succinctly stated on his website, is marine algae. So, but that's obviously just the start of it. He's a biogeochemical cycling expert and ecological modeler, and Mike will tell us about the North Atlantic Aerosol and Marine Ecosystem Study, or NAAMES, funded by NASA. And Mike, please go ahead and take it.
Okay, so can you guys hear me all right?
Yeah, you sound great.
Okay, so the NAAMES project was started in January of 2015. It's a 5-year project, so we're about halfway through. It's part of NASA's, or was funded under NASA's Earth Venture Suborbital Mission Program. All right, so what I prepared for today is pretty high-level overview of the mission, and I assume we have plenty of time for questions afterwards, so if there's details you want, we can do it then. So why NAAMES? Why are we doing this? Obviously, plankton are very critical to the health of oceans, fisheries production. They're important to atmospheric carbon dioxide levels and to the goods and services in general provided by the ocean. NAAMES focuses on hotspots of ocean production, which we often refer to as phytoplankton blooms, that occur in many of the subpolar regions. We don't understand yet how climate and ecological factors control these vital annual phytoplankton blooms and the annual cycles. Plankton ecosystems, as many of you might know, also are important for emitting particles into the atmosphere, or aerosols, and these aerosols can have a significant influence on clouds and climate. So overall, the NAAMES project aims to provide new insights on the function of plankton ecosystems and their connection to atmospheric aerosol clouds and climate. So in NASA parlance, the overarching science goals of NAAMES are to define environmental ecological controls in plankton communities to improve predictions of their structure and function in a warmer future ocean, and to define linkages between ocean ecosystem properties and biogenic aerosols to improve predictions of marine aerosol cloud climate interactions with a warmer future. These overarching goals are then more focused in the baseline science objectives. So the objectives of the project are, number one, to characterize plankton ecosystem properties during primary phases of the annual cycle, and I'll explain that in just a minute. The project is focused in the North Atlantic and looking at their dependence, this annual cycle's dependence on environmental forcing. The second objective is to determine how primary phases of the North Atlantic annual plankton cycle interact to recreate each year conditions for an annual bloom. And so one of the things about the NAAMES project that is, I think, different than previous bloom studies is that it's really trying to look at how plankton blooms function within an overall annual cycle that is somehow recreated every year such that you get a bloom in a predictable time in a predictable manner. And the third objective is to resolve how remote marine aerosols and boundary layer clouds are influenced by plankton ecosystems in the North Atlantic. The science team is very diverse. So this is a list of all the primary co-investigators, and of course each one of these has numerous students and postdocs involved in their groups. I broke it out into 5 basic categories. Project management, so I'm the principal investigator, and all the rest of the project management is at NASA Langley. So they take care of all the business end of the NAAMES project. Project science, ship instruments and ship science, airborne instruments, airborne science, and flight operations. And flight operations are managed out of NASA Wallops. The significance of the red names are these are people that were brought into the NAAMES project after the project was funded. So this is additional funding through various sources to fill out some of the missing or the gaps in the project plan that were in the proposal. They were known gaps, but there was a limited amount of money, so these were brought on with additional funding after the selection. So an overview of the science investigation. The North Atlantic is home of the largest phytoplankton bloom in the world. It is an area of low natural atmospheric aerosols where biogenic aerosols can have a significant impact and have been shown to have long-distance transport. The ecological and physical processes that control bloom development are strongly debated. That debate has been heating up over the last 10 years rather than cooling off. But clearly this bloom, as in many cases blooms are, linked to climate forcings. And so there's a very strong interest in that and how future climate change might impact the North Atlantic blooms and blooms in general. Improved understanding of bloom dynamics and associated aerosols will reduce uncertainty and projections of future change and implications to ocean productivity and climate. And so the project includes numerous modeling activities as well as field work. All right, I'm going to walk through this a little bit slowly so you understand what we're doing. So the NAAMES project has 4 field campaigns. These do not have to be executed in a particular order. The objective is to target 4 specific contrasting phases of the annual plankton cycle and to capitalize on natural gradients or meridional gradients in states of the plankton cycle that exist in the North Atlantic. And that gives us some buffer, I guess you could say, in terms of ensuring that we see these different phases when we are set to a specific cruise schedule. So on the right-hand side of this figure is an annual cycle in the specific rate of change in phytoplankton biomass. So this is the rate at which mixed layer phytoplankton biomass changes at 8-day resolution. And note that the x-axis is split between June and July. So summer is on the far left and far right. So values of the specific rate of change that are positive means that the phytoplankton biomass is accumulating, and values that are negative means that it's declining. So the yellow shading is declining phases, and the blue shading is the increasing phase. And one of the things that I think surprises people about this is that you see that the blooming phase, the blue area, starts actually in the winter. The North Atlantic spring bloom is a phenomenon that gets started in the winter when growth conditions for phytoplankton are at their worst. So we're targeting 4 basic phenomena in the annual cycle. 2 transition periods. These are the times when the rate of accumulation switches sign. So it goes from a decreasing biomass to an increasing biomass, or the other way around. Those transitions occur in November-December timeframe for bloom initiation, and the decline or the climax of the bloom typically happens in the May-June timeframe. And then the other 2 campaigns are targeting accumulation phases and deceleration phases, so kind of the center of the blue area and a major part of the yellow area. So those 2 targeted phases are March and April, and September and October. Okay, so the field campaigns. Each one of the campaigns involves a 26-day shift deployment. We've conducted 2 of these so far. The first one was targeting bloom initiation. It was executed November 5 to December 2nd, 2015, so less than a year after the project started. That was followed up 6 months later by a bloom climax campaign that was conducted May to June 2016. And right now the project is in what I call the intermission period. So it was scheduled into the NAAMES project to have a year-long intermission where we kind of lick our wounds, figure out what we did wrong, figure out what we did right, figure out what's missing, so that when we go into the next 2 campaigns, we're better prepared. So the next field campaign is going to take place this September. We're leaving from Woods Hole on the 30th of August, and we'll be coming back on the 24th of September. And then the final campaign is 6 months later. It's going to be, or it's currently scheduled with UNOLS for the month of March. The ship campaigns basically have a common default profile. They're all based out of Woods Hole. They transect to a primary science line, which is approximately 40 degrees west. And then the primary science line extends from about 40 degrees north to about 57 degrees north. And of course, there is some variability in that based upon conditions during a given campaign. Some of the flexibility built into the project is that we can use a different departure and arrival port. It doesn't matter which way we go around the triangle. So, if weather conditions suggest we should go north to south or south to north, that doesn't really matter. Another thing I wanted to point out here was in the bottom right figure, we actually are essentially setting up our primary stations along the science line in real time, and we're using satellite altimetry data to identify significant mesoscale eddy features and targeting anticyclonic and cyclonic and outside of eddies for different stations, so we can get kind of a sampling of these different types of communities. Ocean biological measurements on the ship are focused on biological composition and stocks, various rate measurements, rates of accumulation and loss processes, aerosols, concentration and production rates of aerosol precursors in the ocean, air-sea transfer, and lower troposphere biogenic aerosol concentrations. And of course, we also have a suite of optical measurements, and this ties the in situ measurements to remote sensing. In addition to the very specific ship-based measurements, we also are deploying floats and drifters. Approximately 3 to 6 of the floats, BioArgo type floats, are deployed each campaign. 20 drifters are deployed as well. These are all deployed at the specific stations. The intent of these autonomous assets is to provide sustained observations pre-campaign, in the sense of going back to ones we deployed earlier, and then post-campaign. And it also enables some information on station targeting. In other words, if we have a float that is occupying a specific eddy, then that eddy moves up in the priority places we would target for a station. The drifters function as a sort of breadcrumb trail. It allows the aircraft measurements to go back to places the ship has occupied and left, and continue following changes in the plankton properties after the ship has departed. And then finally, the floats in particular are enabling evaluation of predictive capabilities from ship measurements. The idea here is trying to answer the question, if I go to a spot in the ocean and I characterize in detail the plankton system and the interactions between division and loss rates and things like that, how far into the future can I predict changes in biomass? Can I only predict it for a week? Can I predict it for a month? That's kind of the question, the ecological forecasting idea with the floats. The Airborne Campaign is using a NASA C-130 aircraft. This was a post-selection assignment to NAAMES. We had originally wanted the P-3, but we got a C-130. I'll talk about the significance of that later. The aircraft campaign is based out of St. John's Bay in Canada. The deployment profile, typically this is, of course, weather dependent and lots of factors dependent, but typically depart from St. John's toward the ship and do transects around the ship, measuring ocean and aerosol properties, and then fly to surface drifter areas, overfly the upcoming transect, and then return to base. Our objective is to achieve a minimum of 6 successful flights per campaign. So the purpose of the aircraft measurements is to link ship aerosol and ocean biological observations to satellite pixel scale. So we always have an issue when comparing in situ data with satellite data in terms of scaling it up. And so the aircraft measurements are trying to assist in that problem. It allows aerosol and cloud sampling upwind and downwind of the ship, so all the aerosol measurements on the ship have some context, as well as some information on fates, and allows spatial variability assessments. The 4 primary instruments on the aircraft are a high spectral resolution LiDAR. This is targeting vertical profiling of clouds and aerosols, as well as subsurface plankton profiling. We have the Research Scanning Polarimeter, RSP, which is looking at column integrated properties of clouds and aerosols, as well as a limited number of plankton properties. GeoCape Airborne Simulator is a hyperspectral ocean color sensor. So its primary objective is to look at plankton and carbon stocks in the ocean. And finally, we have the 4-Star, which is a sky scanning, sun tracking atmospheric instrument. And its primary objective is to characterize downwelling sunlight at the top of the airplane, but also provide some information on atmospheric chemical composition. Satellite support for the mission, certainly ocean color from MODIS and some of the other international sensors. We have had overflights with the Calliope LiDAR, which we've been using recently to derive not only atmospheric properties, but plankton properties. And then, of course, altimetry for eddy characterization. Modeling allows the integration of NAAMES observations into system function and extension of NAAMES results to future forecasts. Our primary modeling components are ocean circulation ecosystem modeling by Scott Doney's group at WHOI, mesoscale processes at the University of Washington, that's Peter Gobb, as well as another investigator at City College of New York. The aerosol modeling component is largely focused at NASA Langley and cloud modeling at University of Washington, Rob Wood there. And we have a nice website. If you are interested, please go and browse that. It has data, has a lot of information on NAAMES. There's also a link there to a feature called Journalist at Sea. If you're interested, on the first campaign, I took a professional reporter out with us, and Nicole Estefan was her name. And she just tried to capture in very simple terms the experience of being at sea and what NAAMES science is all about. And she did a wonderful job, so if you get a chance, definitely take a look at that. In terms of actual measurements, I'm not going to go into all the details. This would be very dry if I did, but the basic philosophy here is to have multiple measurements for key properties. So not necessarily focused on a specific measurement, but a property, and looking at it from many different measurement approaches. So in the case of phytoplankton, for example, we have a number of different ways of measuring phytoplankton biomass, a number of approaches for division rate, loss rate, and accumulation rate. Of course, those 3 rates, you only need 2 in order to figure out the third one. And then also measurements for characterizing ecosystem spatial variability. And this is just an example of the phytoplankton lines. We also have measurements of zooplankton community composition, bacterial diversity, dissolved and particular organic stocks and remineralization rates, viral mortality, phytoplankton diversity, physical and optical properties, and much, much more. Similar for the atmospheres, just looking at some aerosol and clouds. So aerosol gas composition with multiple approaches, aerosol microphysical properties, cloud microphysical properties, continental and anthropogenic influences, and again, spatial variability. And again, measurements also include a diversity of ship-based assessments, and these are trying to provide a thorough characterization of aerosols immediately above the surface ocean, but also transfer from the ocean into the air and in-water aerosol precursors and a variety of other measurements. From the airborne perspective, with the remote sensing instruments, again, looking at properties, not just a specific measurement. So for characterizing ecosystem spatial variability, we're getting information from the HSRL, the RSP, as well as the hyperspectral GCAS. And for aerosols, HSRL, again, RSP, and LARGE are contributed information on that. And LARGE, by the way, is in situ sampling on the aircraft. So they're taking in samples through a nozzle in the aircraft and doing direct measurements of aerosols with LARGE. LARGE is a suite of different instruments. In terms of data, the way this is done is that NASA has very strict requirements on data and data access. Because the NAAMES project is both an ocean ecology and atmospheric aerosol mission, it was decided at NASA headquarters that the data would be separated based on discipline and allocated accordingly to different NASA DACs. So the ship measurements and ocean properties are being managed by Chris Proctor at NASA Goddard, and the data are resident on the OBB DAC. The atmospheric data are being managed by Gao Chen, and they're held at NASA Langley. The data are first, we have a name-specific FTP site that is available only to the investigators, and this is used for immediate download of field data and exchange between investigators, and the data that sit on the FTP site are preliminary. They haven't been CalVal'd or anything like that. So once we get to a stage where we have, relatively good data, then they're staged at a more accessible data site. For the ocean data, there's a 6-month latency for release, and the atmosphere only a month. The difference is because the ocean data just often takes a lot longer to process once the samples get back to the lab. And then all data are required to be uploaded to the NASA DACs within 12 months after the a given field campaign ends. So it's not 12 months after the project, it's 12 months after each campaign. So a little taste of some of the things that we've been seeing. A lot of analyses are going on right now. I mean, we're really starting just during this intermission period to really start pull together the various lines or various stories from the studies. And again, we're only halfway through all the field campaigns, but certainly are seeing some very cool results. The November cruise, as you might expect in the North Atlantic, was rather rough. So we got our butts kicked doing that, but got some great data anyhow. Just a couple of highlights. One of the things we found is consistent with that graph I showed you earlier that was from satellite data showing the annual cycle of the plankton. In November, December, we actually find that phytoplankton concentrations were low, but the populations were diverse and also in very good physiological conditions. There was no indication of physiological stress, even though it was going into winter. The division rates of the phytoplankton were generally greater than the loss rates, and this was a key thing I was looking for. What it means is that, as the satellite had predicted, the blooming phase was actually already starting. We measured some of the lowest aerosols ever recorded, which was very cool to see, and also means that there's a very strong potential influence of aerosol loads that are there on cloud characteristics. The aerosols at that time of year were a mixture of sea salts and continental marine organics, so there was some biogenic organics. The autonomous floats and drifters followed very different trajectories. And this was actually kind of interesting, and we're working on what this actually means in terms of the connection between the surface layer we see from space and the somewhat deeper physical features that give rise to the eddy field. So that's a very interesting story that's developing. Just one little snapshot of some data on the bottom graph. So what you're looking at on the top panel is atmospheric DMS. This was measured from a container on the ship. And at the bottom is the seawater DMS level. And one of the things to note here is the numbers, the atmospheric DMS numbers, the scale goes up to 200. And there's not a lot of correlation between the seawater DMS and the atmospheric features. All right, Campaign 2. Campaign 2 is at the climax of the bloom. A number of really interesting things happened during that cruise. First of all, the phytoplankton concentrations were at a climax. Populations, again, diverse, but surprisingly, diatoms were not dominant. In fact, finding populations dominated by diatoms is very hard to do. It's actually, these climaxes in this part of the North Atlantic, at least during our cruise, were dominated by smaller species. Again, they were all in good physiological condition, even though the blooms were coming to a climax. Another interesting point. Phytoplankton division and loss rates were both proportionately elevated. In other words, even though the division rates of the phytoplankton were much higher than in November, the loss rates were equally enhanced, so that the accumulation rates were often comparable to what we saw in the winter, which is interesting and again consistent with the satellite record. Aerosol levels were elevated with significant biogenic components this time. I'll just skip the last two bullets for a second and look down at the bottom graphs. Again, you're seeing atmospheric DMS in the top panel and seawater DMS in the bottom panel, but note that the scale is now going to 2,000 rather than 200. and the primary features in the top panel are reflected in the bottom panel. One of the very cool things that we ran into during this campaign was we got to witness what I call a disturbance recovery event. So during Station 4, as we were transecting from Station 3 to Station 4, a storm blew through. And by the time we hit Station 4, the water column had been thoroughly mixed down to more than 200 meters. And the concentration of phytoplankton had been greatly diluted by this mixing event, essentially resetting the blooming process. And so, noting that we had run into this fortuitously, we maintained that station for longer than other stations, and were able to document the processes of recovery and the balance between phytoplankton division and loss, the creation of a bloom, and the subsequent elevation of aerosols associated with that bloom. And then finally, at the last station on that cruise, we were right in the middle of we were right in the eye of a storm, and we're recording air-sea transfer at some of the highest wind levels ever recorded. This is just an example from that Station 4 disturbance recovery event. What you're looking at here is in the green symbols fluorescence, which is it's a proxy for chlorophyll concentration with lots of caveats to that, but basically it's showing the rise in the phytoplankton concentration over the course of a few days. And then slightly lagged behind that, the coupling of DMS in the seawater. So a nice vision there of biology and aerosol precursors. This is just an example. So the airborne data, a lot of the airborne data are still being crunched and analyzed, but this is just an example of types of curtains that we see with the HSRL LiDAR. So what you're looking at in the top and bottom panels are two different airplane transects, and each one is divided by a hashed white bar. The top are the aerosols in the atmosphere and their vertical structure, and below that white bar are LiDAR retrievals from under the ocean surface. So these are plankton properties and vertical structure. In the top panel, for example, you'll see that there's kind of a white line in the atmospheric data and a bunch of, it looks like noise below that. What you're looking at there are clouds. So those are clouds that the LiDAR was not able to penetrate. And also at the same locations, you don't get an ocean retrieval, obviously. But when you have the LiDAR penetration right to the ocean surface, you see a corresponding subsurface retrieval. So what are some of the challenges we've met during this mission? The assignment of the C-130 was certainly a challenge. When we got it, it was not prepared for doing science. It was a military aircraft, and so converting that to a science asset increased costs. The operation of the C-130 is more expensive than the P-3. The modification challenge to schedule, which we worked out, but it was right down to the breaking point. And we've also experienced a number of breakdowns, which have had some impact on our science capabilities. Ship scheduling, UNOLS has been fantastic working with the NAAMES project, getting the ship scheduling to work. But because we are targeting fixed features in the annual cycle, it challenges the flexibility within UNOLS scheduling. And as NAAMES proceeds, the challenge gets more difficult because we've already, right now, we've got 2 of the seasons. We're only left with 2, and we start running into really having little flexibility in terms of when we go out on the last campaigns. Cloudiness, we anticipated cloudiness to be an issue for remote sensing, but it has been a greater issue than we had anticipated. So getting a good set of ship and aircraft matchups has been a challenge. But we've gotten some good data, but at certain times we were not. For example, at Station 4, I don't think we got any aircraft data while the ship occupied that, which was unfortunate. And then there's always just the general challenge of interdisciplinary science, trying to get, even with everyone's good intention to do so, just getting data exchange to be efficient and timely, and communications between scientists and different disciplines. It's just always something you have to keep nurturing. And one of the things we're doing to make sure that happens is during the intermission period, we have monthly telecons. We broke the team up into 6 different sub-elements, And then we have a monthly tag-up. And before the monthly tag-up, each of the sub-elements has their own telecon to kind of update where things are at, and then they report out to the team. And that has been very good for continuing to move the science of names forward during the intermission and not letting it, fall off the table until the next campaign. Okay. Hope that was helpful.